I'm Sahar and my poster presents our work on warped gravitationally unstable protoplanetary disks. In the last few years, as the number of observed protoplanetary disks have increased, it's clear that a large majority of bright large disks are axisymmetric, with some also having ring and gap structure. A rare few disks instead show large-scale spar structures which are thought to be formed by gravitational instability. Gravitational instabilities typically occur in young disks when they're still massive enough for self-gravity to play a key role in its evolution. However, even observations of very young disks tend to reveal ring and gap structure. Our aim is to give a plausible explanation to why gravitationally unstable disks are rarely seen. These disks may be warped by inclined companions, flybys, or chaotic misaligned infall. For the first time, we consider a warp in a self-gravitating disk, starting with an idealized warp. We show that additional heating induced by a strong enough idealized warp can suppress spar structures due to gravitational instability, resulting in an axisymmetric disk more in line with observations.
Why is it that radiative transfer simulations of H-alpha emission from T-Tauri stars perform well, yet the same models struggle to predict the observed infrared emission? My name is Tom Wilson, and I'm exploring hydrogen emission from T-Tauri stars. I'm using and developing the radiative transfer code torus to create synthetic line profiles. I'm currently working on a grid of radiative transfer models covering a broad range of accretion and outflow parameters. To ground my synthetic emission in reality, I have the spectra of 29 T-Tauri stars on X-Shooter. This gives me near simultaneous observations of both the visible and infrared hydrogen lines. I have found that I can recreate the expected and the observed H-alpha intensity and spectral features. However, when I take those same models that do so well for H-alpha and calculate the synthetic emission for the infrared lines, my models behave poorly. The infrared emission I have been examining are systematically too thin and highly structured. For example, the models exhibit a frequency of inverse P Cygni profiles of more than 80%, a stark contrast to what is observed. This result is an intriguing problem. Why is it that our models predict such structured emission, and what mechanisms can be invoked to broaden the infrared lines?
Hello everybody, and thanks a lot for listening to me. My name is Etienne Martell, and I am a third-year PhD student under the supervision of Geoffroy Lezure at IPAG in Grenoble. I work on numerical simulations of transition disks with magnetized winds. I guess you've all heard about protoplanetary disks, and especially about transition disks, which are protoplanetary disks that exhibit a cavity in the dust and the gas density profiles. I report the results of the first global simulations of transition disks with MHD winds in the context of non-ideal MHD. Astonishingly, transition disks accrete roughly as much matter as protoplanetary disks, which are full disks. The model I use, with magnetized winds, accounts for such high accretion rates, and that's only one of the results I get with it. If you want to get more information, do not hesitate to check my poster. Thanks a lot, and goodbye.
Hi, my name is Barbara, and my poster is titled An Ongoing Investigation on the Ejection Processes in a Young Open Cluster NGC 65. Here, I present to you a brief summary of the poster contents. The main goal of this work is to investigate possible correlations between the properties of the oxygen-1 forbidden line at 6,300 angstroms, a well-known tracer of winds and jets, and properties of the star disk systems in the sample. The sample consists of high-resolution flame spectra of 274 stars located in the region around NGC 65. Positive detections of the oxygen-1 line so far include 17 classical T-Tauri stars, 1 Hebig AEBE star, 1 class 0/1 young stellar object, as well as 16 stars with unidentified classification. Here, you can see some examples of the detection found so far, which include slow winds traced by the low velocity components as seen here on the left side of the screen. Other examples of detection are seen on the right side, and multiple ejection features here on the top right, as well as double-peaked line profiles seen here on the bottom. Details on these and two other profiles can be seen on my poster available at SEMA. Thank you for your attention and have a
Hello everyone, in this poster presentations I will talk about the formation of catastrophic cooling outflow in star forming regions, and we did a non-equilibrium hydrodynamic radiative simulations, and we found the region where the catastrophic cooling happens. Typically we have adiabatic solutions, however we extended this adiabatic solution and we did included radiative cooling functions, and through a hydrodynamic simulation we found the region where catastrophic cooling happens. Here you see the simulation of the result of our simulations, and we see the formation of the catastrophic cooling beams in region with low terminal velocity, and also we consider the metallicity and how metallicity affect catastrophic cooling. We see higher metallicity, we have higher coolings, and we also consider the mass loading rate. By increasing mass loading rate, we increase the region where catastrophic cooling happen. And in this link you can look at the results, and we also did emissivity calculations. Thank you for your attention, and see you later.
Hello, I'm Jen from University of Hertfordshire. My poster is about large amplitude periodic outbursting vessels discovered in the VVV field. The mass accretion process is highly unstable during the protostellar stage, such as unpredictable EXO rays and FU array type outbursts. As a consequence of dynamical perturbation from a stellar or planetary mass companion, several periodic outbursting protostars were discovered in the literature. In this work, we found 61 high-amplitude periodic outbursting vessel candidates from the VVV database, which is an order of magnitude enlarged of the total known sample of such kind of sources. The pure rate of these targets range from 16 to 1,000 days, indicating the location of the perturber is either at the inner edge of circumstellar disk or extending out to several AUs. We also found that most high-amplitude variables are faster bursters with a rapid outbursting stage and a slower decaying stage, as shown in the bottom left of the plot. We are working on spectroscopy follow-up studies to investigate the possible binarity on these sources. This work proposed some indirect evidence of the existence of a young planet, and also proposed many theoretical challenges to the community. If you are interested in my work, please go to check the poster. Thank you.
Hello everyone, I'm Yolan, a medical postdoc fellow at University of Virginia. I would like to talk about an outflow study using 0163 micron emission in L351 RS5. This paper has been submitted to APJ recently. Outflow are a primary mechanism to remove angular momentum in collapsing core, facilitating the growth of protostars. Atomic lines such as O1 better probe the current status of outflow. However, the line profile O1 cannot be resolved until SOFIA. The upgrade instruments on SOFIA allow us to finally resolve the O1 line profile to investigate ongoing outflow activities. In this study, we observed 3 positions along the outflow of L251 RS5, center, red, and blue. Given our sensitivity, we only detect and resolve O1 emission toward the protostar with SOFIA. The symmetry line profile O1 immediately caught our eyes, and we argued that higher extinction toward the redshift outflow can block the redshift emission. With that in mind, we further decomposed the O1 line profile into broad components at the source velocity, which can be due to cavity shocks or disk swing, and an offsetting extremely broad component, which is likely come from jets. Comparing to the archival water and high JCO lines, the atomic oxygen actually dominated the total oxygen budget. From the extremely broad components, we further measure the intrinsic outflow rate, which is consistent with that derived from CO and H1 with momentum conserved outflows. We also find no significant variability of the intrinsic outflow rate. Please check out my poster for more detail.
The title of the poster is Accretion Bust in High-Mass Young Stellar Objects. The latest picture of YSO evolution suggests that a large portion of their final mass might be actually gathered during accretion bust. Indeed, most recent observations have strengthened our idea that episodic accretion is a common universal phenomenon across mass and time in star formation. The study of episodic accretion in high-mass YSOs is just begun, and in the past 6 years, we have been detecting 8 of such episodes. 4 bona fide bursts, 2 more from possibly massive protostars in the making, and 2 more from massive periodic outbusters, such as this one here. Despite the small sample, a large variety of physical properties has been observed, similarly to low-mass YSO bust. However, released energy, mass accretion rates, and accreted mass of such episodes are orders of magnitude larger than in low-mass YSOs. Besides photometric and spectroscopic variability, these busts are also traced by methanol and water maser flares or radiojet bursts. Finally, here in this poster, we also show time-dependent radiative transfer models that match the observed SED variations and try to explain how these bursts affect the circumstellar environment of these outbursters. Thank you very much.
Hello everyone, my name is Bakken, and I want to discuss the possible scenarios explaining the recently observed outburst on high-mass young stellar objects with masses more than 10 solar masses. We find that disks around these high-mass young stellar objects are hotter than the ones around their low-mass cousins. And as a result, much more extended region of a disk is prone to the thermal instability and magnetorotational instability, which trigger an accretion outburst. And these accretion outbursts, however, have lower peak accretion rates and 1 to several orders of magnitude longer than those observed on high-mass young stellar objects. Thus, these accretion bursts are unlikely to result from the hydrogen ionization and MR activation instabilities. On the other hand, a burst generated by the tidal disruption of gaseous giant planets formed by the gravitational instability in the disk are consistent with the observations and can explain observed characteristics very well. If you are interested, please take a look at our paper that is published and hope to see you soon all on the conference. Thank you.
Hello, my name is Anton Finio Hansen, and I have a poster on a high-resolution radio study that we did on L1551 IRS5. This is a binary class 1 system that we observed in the Taurus molecular cloud using VLA and eMerlin last year. So we compared the images that we obtained with previous observations from 2002, and we see that there has actually been significant variability in the jet emission from both components in the system. For example, in the northern jet, it looks like the radio jet has almost entirely disappeared over the last 20 years as the flux density has dramatically decreased, while in the southern source, the flux density is actually increased. We also combined our data with previous ALMA data to model the emission from both the jet and the disk over a wide range of frequencies. And we see again here in the northern source, it looks like there's almost no jet emission, and it's almost entirely just dust emission from the disk. While in the southern source, we clearly see jet emission, including both optically thin and thick emission. Thank you for your attention, and if you want to learn more, please check out my poster. Thank you.